In the quiet moments before sleep, when the mind drifts between waking thought and unconsciousness, there exists a space where the comfortable certainties of everyday life begin to dissolve. It is in this liminal state that the universe reveals itself not as the orderly, predictable system we navigate during daylight hours, but as something far stranger, far more unsettling, and ultimately far less noble than we typically allow ourselves to consider. If you find yourself drawn to these questions, to the edge of what can be known, consider watching in full-screen mode and subscribing to follow this exploration further. What follows is an examination of the boundaries where human understanding meets its limits, where the equations that describe reality begin to suggest outcomes that challenge not merely our knowledge, but our capacity to maintain psychological equilibrium in the face of what those equations imply. The universe operates according to principles that remain largely hidden from casual observation. We live our lives on the surface of a spinning planet, held in place by forces we cannot see, breathing air composed of molecules we cannot perceive, our bodies regulated by biological machinery operating far below the threshold of conscious awareness. This invisibility of mechanism is not merely a feature of everyday life, but extends into the deepest levels of physical reality itself. The theories that scientists develop to explain this reality are not simple descriptions, but complex mathematical structures that predict, with sometimes unsettling accuracy, phenomena that violate intuition and comfort in equal measure. Yet among these theories, certain implications emerge that are discussed rarely, if at all, in public discourse. This silence is not always a matter of ignorance or conspiracy, but often reflects something more subtle, a recognition that certain ideas, once fully articulated and understood, carry psychological weight that extends beyond the merely academic. Consider first the nature of consciousness itself, not as philosophers have traditionally approached it, but as a problem within physics and information theory. The human brain is a physical system composed of approximately 8 to 6 billion neurons, each connected to thousands of others through synaptic junctions that transmit electrochemical signals. These signals, when measured, produce patterns of electrical activity that can be recorded, analyzed, and to some degree predicted. The brain operates according to the laws of physics, the same laws that govern the motion of planets, the behavior of atoms, and the flow of energy through all physical systems. There is no evidence of any non-physical substance or force acting within the brain, no indication that consciousness requires anything beyond the ordinary matter and energy that constitutes all other objects in the universe. This materialist picture of mind has been gradually solidifying over centuries of neuroscientific investigation, each advance removing another piece of explanatory territory that might have harbored some special, non-physical essence of selfhood. But this materialist understanding, when followed to its logical conclusion, generates a profound and rarely articulated problem. If consciousness is entirely the product of physical processes in the brain, and if those physical processes are entirely determined by prior physical states and the laws of physics, then consciousness itself, including the experience of making decisions, of exercising will, of choosing one action over another, must also be entirely determined by prior physical states. The feeling of free will, the subjective sense that we are the authors of our own choices, becomes in this framework not a fundamental feature of reality but an illusion generated by a brain that cannot perceive its own determinism. The physical processes that produce the experience of deciding occur before the conscious experience of decision-making, as has been demonstrated in numerous neurological experiments where brain activity predictive of a choice can be detected several seconds before the subject reports awareness of having made that choice. This creates what might be called the problem of causal impotence. If our conscious experience does not cause our actions but merely accompanies them, arising as a kind of narrative constructed after the fact by brain processes that operate below the threshold of awareness, then consciousness is epiphenomenal, a side effect without causal power. We do not choose our thoughts. Our thoughts arise from physical processes we do not control. We do not decide our actions. Our actions flow from neural states that were themselves determined by prior states extending back through our entire history and ultimately back to the initial conditions of our brain's development and the environment that shaped it. The person you believe yourself to be, the agent who seems to guide your life through a series of chosen actions, is a story told by a physical system that operates according to mechanical principles. Scientists working in neuroscience, cognitive science, and the philosophy of mind are acutely aware of these implications, yet they are rarely discussed in full outside specialized academic contexts. The silence surrounding this issue is not complete, of course. There are papers, conferences, and books that address determinism and free will. But the full psychological and social implications of a thoroughly deterministic understanding of human behavior remain largely unexamined in public discourse. This reticence may stem from recognition that human social systems, legal frameworks, concept of moral responsibility, and perhaps even individual psychological stability depend on maintaining the intuition that people are, in some meaningful sense, the authors of their own actions. To thoroughly internalize the understanding that all behavior is the inevitable output of physical processes could undermine the conceptual foundations on which societies are built. Yet the scientific evidence continues to accumulate, each study further constraining the space in which free will might operate. Brain imaging studies show that neural patterns associated with decision-making begin to form well before conscious awareness. Genetic studies reveal the extent to which behavior is heritable, determined by factors entirely beyond individual control. Psychological research demonstrates how dramatically behavior can be influenced by situational factors, priming effects, and unconscious biases that the individual cannot perceive and therefore cannot counteract through conscious choice. The space for autonomous agency grows smaller with each advance in understanding, until it becomes difficult to identify any level of analysis at which something that could genuinely be called free will could operate. Some have argued that quantum indeterminacy might provide a foundation for free will, that the inherent randomness at the quantum level could translate into genuine openness in neural processes. But randomness is not the same as choice. If neural processes are random rather than determined, this does not grant the conscious self any greater control. It merely replaces deterministic causation with stochastic causation. The experience of willing an action, of it being my action flowing from my choices and values, is not preserved by introducing randomness into the system. Random actions are not free actions. They are simply uncaused actions, which is arguably worse from the perspective of moral agency and personal identity. The implications extend beyond individual psychology into the structure of society itself. Criminal justice systems are predicated on concepts of moral responsibility that assume genuine agency. Punishment is justified by the notion that the criminal chose to commit the crime and could have chosen otherwise. But if all actions are the deterministic consequences of prior physical states, then no one could have acted differently than they did, given the exact physical conditions that obtained at the moment of action. This does not necessarily mean that punishment is unjustified, but it would require a complete reconceptualization of its purpose. Punishment could be understood as a form of environmental modification, a way of altering the conditions that produce certain behaviors, but not as something the criminal deserves in a deep moral sense. The satisfying feeling of righteous judgment, the sense that justice has been served when a wrongdo suffers, becomes harder to justify when the wrongdo is understood as a physical system that could not have done otherwise. Similarly, concept of personal achievement and merit become problematic. If all your choices and actions flow deterministically from conditions you did not choose, your genetic endowment, the circumstances of your upbringing, the sequence of experiences and influences that shaped your neural architecture, then in what sense do you desire credit for your accomplishments? You did not choose your intelligence, your personality, your talents, or the circumstances that allowed you to develop and apply them. The distribution of success and failure in human society, when viewed through the lens of determinism, begins to look less like a just allocation based on merit, and more like an arbitrary outcome of causal chains that could have been otherwise only if the initial conditions had been different. Yet people continue to live as if they possess free will, and perhaps they must. The phenomenology of decision-making is so compelling, the experience of deliberation and choice so central to human consciousness, that it may be psychologically impossible to fully internalize a deterministic worldview at an emotional level, even if one accepts it intellectually. Scientists who study these questions often report exactly this disconnect, acknowledging that they cannot shake the feeling of agency even while recognizing it as an illusion. This might represent a fundamental limitation of human cognition, an inability to perceive our own nature clearly because the architecture of consciousness itself requires the illusion of agency to function. There is something deeply unsettling about this possibility, that we are built in such a way that we cannot see ourselves clearly, that accurate self-understanding is prevented by the very structure of the self that seeks understanding. It suggests that human beings might be fundamentally alienated from their own nature, capable of grasping intellectually what they cannot integrate experientially. The scientific method, which has proven so powerful at revealing the nature of external reality, turns back on the scientist and reveals something about the nature of mind that mind cannot fully accept about itself. This creates a strange doubling, a space where intellectual understanding and lived experience cannot be reconciled, where the person becomes split between what they know and what they feel, unable to bridge the gap. The silence of scientists on this matter, then, is perhaps not really silence but hesitation, a recognition that this knowledge, while seemingly secure on empirical and theoretical grounds, carries consequences that are difficult to navigate. How does one live in full acknowledgement of determinism? How does society function if this understanding becomes widespread? These are not merely philosophical questions, but practical ones, touching on the stability of social systems and individual psychology. The knowledge sits uneasily, discussed in specialized contexts, but rarely translated into the kind of clear public communication that characterizes scientific consensus on less fraught topics. Moving from the internal world of consciousness to the external world of physical reality, another deeply unsettling set of ideas emerges from cosmology, from the study of the universe at its largest scales. The universe, as best current observations and theory indicate, began approximately 13.8 billion years ago in an event commonly called the Big Bang. But this term is somewhat misleading, suggesting an explosion in space. What occurred was rather the beginning of space itself, the emergence of the space-time manifold from a condition that cannot be adequately described using the normal language of physics. Prior to a certain threshold called the Planck time, approximately 10 to the negative 43 seconds after the initial singularity, the known laws of physics break down, and it becomes impossible to make predictions or even formulate meaningful questions about what were happening. Time itself, as a dimension of the physical universe, began with the Big Bang. There was no before, no preceding cause in any temporal sense, because time is a feature of the universe that began at that moment. The universe, having begun, has been expanding ever since, space itself stretching and carrying galaxies along with it. This expansion was initially expected to slow down over time due to gravitational attraction between all the matter in the universe. Gravity, being an attractive force, should cause the expansion to decelerate, possibly eventually reversing into a contraction that would end in a big crunch, a collapse back into the singular state from which the universe emerged. For decades, cosmologists debated whether there was enough matter in the universe to eventually halt and reverse the expansion, or whether it would continue expanding forever, gradually thinning out until all structure dissolved into isolated particles separated by vast distances. Then, in the late 1990s, observations of distant supernovae revealed something entirely unexpected. The expansion of the universe is not slowing down, it is accelerating. Galaxies are moving away from each other at an ever-increasing rate. This acceleration requires some form of energy that pervades space itself, exerting a kind of negative pressure that drives expansion rather than slowing it. This energy has been termed dark energy, though the name is merely a placeholder for ignorance. Its nature remains one of the deepest mysteries in physics. It makes up approximately 68% of the total energy content of the universe, yet it cannot be directly detected, only inferred from its gravitational effects on the expansion rate. The existence of dark energy has profound implications for the ultimate fate of a universe. If the acceleration continues, as current models suggest it will, then the universe will expand forever at an ever-increasing rate. Over immense timescales, this leads to what cosmologists call the Big Rip, or, in a somewhat less catastrophic scenario, heat death. In the heat death scenario, the universe continues expanding until all structure breaks down. Galaxies become isolated from each other as space expands faster than light can travel between them. Within galaxies, stars exhaust their fuel and die, leaving behind white dwarfs, neutron stars, and black holes. These remnants themselves gradually decay through various quantum processes. Protons, if they are unstable as some theories suggest, eventually decay into lighter particles. Even black holes, through a process called Hawking radiation, gradually evaporate over timescales of 10 to the 100 years or more. The universe asymptotically approaches a state of maximum entropy, a cold, dark, nearly empty expanse in which no complex structures can exist and no processes that could be called life or thought can occur. This is the heat death of the universe, a state of absolute finality. It is not merely the death of humanity or even of all life, but the death of the possibility of life, of complexity, of any process that involves the organized transformation of energy. Time continues in some formal sense, but nothing happens. The universe reaches thermodynamic equilibrium and remains there, unchanging, for the infinite duration that follows. Every thought that has ever been thought, every experience that has ever been felt, every structure that has ever existed becomes not just ended but rendered permanently impossible to reconstitute. The universe forgets utterly that anything was ever different. Scientists understand this fate with considerable confidence. The thermodynamics are clear. The observations support it. And while details may change with better understanding of dark energy, the broad picture of eventual heat death is difficult to avoid given what is known about physics. Yet this knowledge is rarely foregrounded in public discussions of cosmology. Popular science tends to focus on the wonder of the Big Bang, the beauty of cosmic structure, the possibility of finding life elsewhere in the universe. The ultimate fate is mentioned, if at all, as a distant abstraction, something too remote in time to carry emotional weight. But the remoteness in time does not diminish the logical implication. If the universe ends in heat death, then everything that occurs between now and then is, in a certain sense, futile. Not futile in the way that failing to achieve a goal is futile, but futile in a deeper sense. Every achievement, every purpose, every value is temporary not just in the sense that it will end, but in the sense that it will end in a condition where it is as if it never happened. The universe will reach a state from which no information about our current state can be extracted, a condition of total erasure. Human extinction is not even the relevant event here. It is the extinction of the possibility that anything we do could matter beyond the finite window in which complex structures can exist. This creates a kind of cosmic nihilism, a recognition that purpose and meaning, if they exist at all, must be constructed locally and temporarily within a universe that is fundamentally indifferent and ultimately destructive of all value. Some philosophers and physicists have tried to find solace in the idea that the journey matters even if the destination is oblivion, that meaning is not diminished by impermanence. But this requires a certain willful act of perspective-taking, a decision to value experience despite its ultimate erasure. It is a defensible position, perhaps the only psychologically viable position, but it is not one that follows from physics. Physics tells us only that the universe will end in a state where nothing matters because nothing can matter, where the substrate for mattering is dissolved into thermal noise. The silence around this implication is partial and strategic. Cosmologists discuss heat death in technical contexts, but there is little effort to explore its philosophical and psychological ramifications in detail or to communicate them widely. This may reflect a recognition that existential despair is not a useful state of mind for a species that must continue functioning, must continue making plans and building civilizations despite their ultimate futility. The knowledge is available to anyone who seeks it out, but it is not actively pushed into public consciousness in the way that more immediate scientific concerns are. There is a tacit understanding that this particular truth, while scientifically robust, is psychologically corrosive and socially useless. Yet the corrosion occurs regardless, slowly, in the minds of those who take the time to fully absorb the implications. The universe's indifference is not a metaphor or poetic exaggeration, but a literal description of physical reality. The processes that generate stars and galaxies, that allow for planets and life and consciousness, are temporary fluctuations in a system that is relaxing toward equilibrium. We are brief eddy currents in an entropy gradient, temporary pockets of low entropy that will dissipate when the gradient flattens. This is not a judgment or a punishment. It is simply the mechanical operation of physical law. But to live with this knowledge, to fully internalize it, is to experience a kind of groundlessness, an absence of ultimate justification for anything. Perhaps related to this cosmic perspective, though operating on very different scales, is another set of unsettling ideas emerging from the study of complexity and systems theory, particularly as applied to human civilization. Human societies are complex adaptive systems, networks of individuals interacting according to rules that produce emergent properties at the collective level. These emergent properties, things like economic systems, political institutions, cultural practices, technologies, are not designed by any single mind but arise from the distributed interactions of many individuals, each pursuing local goals with limited information. The system as a whole exhibits behaviors and dynamics that cannot be predicted simply from knowledge of individual behavior. Complex systems of this type exhibit certain characteristic behaviors. They can exist in multiple stable states, called attractors, and transitions between these states can be sudden and difficult to reverse. Small changes in conditions can sometimes produce large changes in system behavior, a phenomenon known as sensitivity to initial conditions, or, more colloquially, the butterfly effect. Complex systems can also undergo phase transitions, where the entire qualitative character of the system changes. These transitions are often preceded by subtle warning signs, like increased variance in certain measured quantities, but predicting the exact timing and nature of the transition is typically impossible due to the system's complexity. Human civilization, viewed as a complex system, is currently in a state that exhibits several concerning features. The global human population has grown exponentially over the past few centuries, from around 1 billion in the early 1800s to nearly 8 billion today. This growth has been enabled by technological advances, particularly in agriculture, medicine, and energy production, that have dramatically increased the carrying capacity of the environment. However, this carrying capacity is not fixed but depends on complex interactions between technology, resources, and environmental conditions. The exponential growth phase cannot continue indefinitely on a finite planet, and the transition to a stable or declining population could occur through a managed reduction in birth rates or through a catastrophic increase in death rates. History suggests that complex systems often transition between stable states through crisis rather than through smooth, managed adjustment. The global economic system exhibits similar concerning dynamics. It is predicated on continuous growth, with financial systems structured in ways that require increasing production and consumption to remain stable. Debt, which is central to modern finance, represents a claim on future production. If future production does not materialize at expected levels, debts cannot be repaid, and the financial system becomes unstable. Yet continuous growth in material production and consumption on a finite planet faces obvious physical limits. Resources are finite, environmental sinks for waste are finite, and while technology can improve efficiency, thermodynamics places hard limits on what efficiency gains can achieve. The system requires growth to avoid collapse, but growth cannot continue indefinitely, creating a bind from which there is no obvious exit. Environmental changes add another layer of instability. The climate system is a complex system in its own right, with multiple feedback loops and tipping points. Human activity has altered the composition of the atmosphere, increasing the concentration of greenhouse gases to levels not seen for millions of years. This is driving changes in global temperature, precipitation patterns, sea levels, and the frequency of extreme weather events. These changes are not linear or gradual, but involve complex feedbacks that can amplify warming. For example, as Arctic ice melts, the darker ocean surface absorbs more solar radiation, which causes more warming, which causes more melting. As permafrost thaws, it releases methane, a potent greenhouse gas, which causes more warming, which causes more thawing. These feedback loops can create self-reinforcing dynamics that drive the system toward a different stable state, one that may be much less hospitable to human civilization. The question that emerges from this analysis, but is rarely stated explicitly, is whether human civilization is approaching systemic transition, a phase change from the current growth-oriented, energy-intensive configuration to something else. The nature of that something else is unclear. It could be a managed transition to a sustainable, steady-state economy, though achieving this would require coordinated global action on a scale never before attempted and would involve accepting limits to material growth that run counter to the incentives built into current economic and political systems. Alternatively, the transition could occur through collapse, a rapid breakdown of the complex systems that support large-scale civilization, resulting in dramatic reductions in population, loss of technological capacity, and fragmentation of global networks. Collapse is a loaded term, often associated with sensationalism and doomsaying, but it is also a technical concept in the study of complex systems. Collapse refers to a rapid simplification of a complex society characterized by loss of centralized control, decline in economic integration, reduction in specialization, and decreased information flow. Societies have collapsed before: the classic Maya civilization, the Western Roman Empire, the Khmer Empire, among others. These were not primitive societies but complex, sophisticated civilizations that underwent rapid transitions to much simpler organizational forms. The causes varied, but often involved some combination of environmental degradation, resource depletion, economic stress, and political instability, factors that interacted in complex ways to overwhelm the society's adaptive capacity. Contemporary global civilization is vastly larger and more complex than any historical civilization, but this may make it more, not less, vulnerable to systemic crisis. Complex systems can be fragile, their robustness in the face of small perturbations coexisting with brittleness in the face of large shocks or cascading failures. Global supply chains, for instance, are highly efficient under normal conditions but can be severely disrupted by localized crises, as has been demonstrated repeatedly in recent years. Financial systems are tightly interconnected, allowing rapid propagation of instability from one region to another. Information systems, while enabling coordination, also enable the rapid spread of misinformation, social contagion, and destabilizing feedback loops. Scientists working in fields related to sustainability, complex systems, and environmental science are acutely aware of these risks. There is a substantial literature on planetary boundaries, tipping points, systemic risks, and civilizational collapse. Yet public discourse on these topics tend to oscillate between complacency and panic, with relatively little space for the kind of sober, clear-eyed assessment that the situation demands. Part of the difficulty is that the probability and timing of systemic crises are inherently uncertain. Complex systems are difficult to predict, and while certain trends are clearly unsustainable, the exact trajectory of future developments depends on a vast number of interacting factors, including technological developments, policy choices, and random events. This uncertainty creates a communication challenge. Scientists are trained to be cautious in their claims, to acknowledge uncertainty, to avoid overstating what is known. But in the context of systemic risk, this caution can be misinterpreted as reassurance. If scientists cannot say with certainty that collapse is imminent, the public may conclude that there is nothing to worry about. Yet the absence of certainty is not evidence of safety. It is simply an acknowledgement of the limits of predictive capacity in complex systems. The scientifically appropriate stance is to recognize that current trajectories pose serious risks, that the probability of major systemic disruptions is non-trivial, and that the consequences of such disruptions could be severe, even if the exact form and timing cannot be predicted. The silence, such as it is not complete but is rather a kind of muted alarm, a signal that struggles to be heard over the noise of daily concerns and the optimism bias that seems to be a feature of human psychology. People are remarkably good at normalizing risks, at continuing with business as usual even in the face of clear danger, as long as the danger is not immediate and tangible. The slow-motion nature of processes like climate change and resource depletion makes them psychologically easy to discount, even for people who intellectually understand the severity of the situation. There is also a political dimension to the silence. Systemic critique, particularly critique that suggests fundamental limits to growth and the possibility of civilizational collapse, is not welcomed in political systems that depend on promises of continued improvement and prosperity. Politicians who acknowledge deep structural problems without offering easy solutions risk being marginalized. Economic interests tied to the status quo have strong incentives to downplay risks and to promote narratives of technological optimism and market efficiency. The result is that the range of acceptable discourse in mainstream politics is narrower than the range of scientifically plausible futures, leaving a gap between what scientists understand and what policymakers are willing to seriously consider. Shifting focus again, from the systemic to the deeply fundamental, another source of profound unease emerges from the heart of physics itself, from quantum mechanics and its implication for the nature of reality. Quantum mechanics is the most successful physical theory ever developed, making predictions that have been confirmed with extraordinary precision across a vast range of phenomena. It describes the behavior of matter and energy at the smallest scales, the scales of atoms and subatomic particles, and it does so using mathematical structures that are conceptually very different from the classical physics that describes everyday experience. In classical physics, objects have definite properties at all times. A particle has a definite position and a definite velocity, whether or not anyone is observing it. Measurement reveals these pre-existing properties. It does not create them. In quantum mechanics, this picture is fundamentally incorrect. Prior to measurement, quantum systems are described by wave functions, mathematical objects that encode probabilities for different possible measurement outcomes. The wave function evolves according to a deterministic equation called the Schrödinger equation, but it does not describe definite states. Rather, it describes superpositions, states where the system is in a combination of multiple possibilities simultaneously. When a measurement is made, the wave function collapses, and one of the possible outcomes becomes actual. This is deeply strange. The most straightforward interpretation is that particles do not have definite properties until they are measured. A photon does not have a definite position until its position is measured. It exists in a superposition of possible positions. An electron does not have a definite spin along a given axis until spin is measured. It exists in a superposition of spin up and spin down. The properties of the system are brought into being by the act of measurement. This raises immediate questions. What constitutes a measurement? What makes a measurement special compared to other physical interactions? Is consciousness required for collapse, or can unconscious physical systems cause collapse? These questions, collectively known as the measurement problem, remain unresolved despite nearly a century of debate. Different interpretations of quantum mechanics offer different answers, but none is entirely satisfying, and none has achieved consensus. The Copenhagen interpretation, historically dominant, treats measurement as a primitive concept and does not attempt to explain what constitutes a measurement or why collapse occurs. It simply posits that the quantum and classical realms operate according to different rules, with measurement marking the boundary. This is operationally successful but conceptually unsatisfying, as it leaves the nature of that boundary unexplained and introduces a kind of dualism between observer and observed. The many worlds interpretation avoid collapse by proposing that all possible measurement outcomes actually occur, each in a different branch of continually splitting universe. When a quantum measurement is made with two possible outcomes, the universe splits into two branches, one for each outcome, and both exist simultaneously in a vastly larger structure called a multiverse. This interpretation is deterministic and requires no special role for measurement, but it posits an extravagant ontology in which infinitely many copies of every observer exist, each experiencing a different history. It also faces a problem of making sense of probability. If all outcomes occur, why do we experience some as more probable than others? Pilot wave theories, such as the Broglie-Bohm mechanics, propose that particles do have definite positions at all times, guided by a wave that evolves according to the Schrödinger equation. This restores a kind of realism, but the guiding wave is non-local, meaning that the motion of a particle can be instantaneously affected by events at arbitrary distances. This non-locality is not unique to pilot wave theories. It is a generic feature of quantum mechanics, demonstrated by violations of Bell's inequalities. Quantum systems can be entangled, such that measuring one system instantaneously affects the state of another system, no matter how far apart they are. This does not allow faster-than-light communication, but it does mean that the universe is fundamentally non-local, that distant regions of space are connected in ways that defy classical intuitions about separability. The implications of quantum mechanics for the nature of reality are profound and disturbing. One implication is that reality may not be fundamentally real in the sense that we intuitively understand. If properties do not exist until they are measured, then the universe is not a collection of objects with definite features existing independently of observation. Instead, it is something more like a web of potentialities that actualize through interaction. This challenges a common-sense realist view that the world is out there, independent of us, with features that exist regardless of whether anyone observes them. Another implication concerned determinism and predictability. While the Schrödinger equation is deterministic, the outcomes of measurements are not. Quantum mechanics is fundamentally probabilistic. It can predict only the probabilities of different outcomes, not which outcome will actually occur. If this randomness is fundamental, not merely a reflection of ignorance, then the universe is not deterministic at the deepest level. This randomness is not the kind that could support free will, as discussed earlier, but it does mean that the future is not entirely determined by the past. There are multiple possible futures, and which one actualizes is a matter of chance, at least at the quantum level. Yet another deeply unsettling feature is the implication for locality and separability. Classical physics assumes that objects are localized in space, that they have definite boundaries, and that distant objects can interact only through intermediate mechanisms that propagate at or below the speed of light. Quantum mechanics violates this. Entangled systems are not separable. They form a unified whole even when spatially separated, and measuring one part instantaneously affects the other part. This suggests that the notion of independent, localized objects is an approximation that breaks down at the fundamental level. The universe is not a collection of separate things, but a holistic structure in which everything is in some sense connected to everything else. These features of quantum mechanics have been experimentally confirmed beyond any reasonable doubt. Entanglement is real, non-locality is real, and the violation of Bell's inequalities has been demonstrated in numerous experiments. Yet the conceptual implications remain deeply unresolved. Physicists use quantum mechanics with extraordinary success, but there is no consensus on what it means, on what kind of reality it describes. This is a remarkable situation. The most fundamental and successful theory in physics leaves the nature of reality itself ambiguous. Scientists are not exactly silent about these issues. There is a large literature on the interpretation of quantum mechanics, and many physicists and philosophers of physics work on these problems. But there is a certain weariness in the field, a sense that the interpretive questions may be intractable or even meaningless, that what matters is the ability to make predictions, not the metaphysical picture behind them. This instrumentalist attitude is pragmatic, but leaves a conceptual gap. If quantum mechanics is true, and it appears to be, then reality is deeply strange in ways that are not fully understood and may not be understandable using concepts developed for navigating the macroscopic world. The strangeness extends even further when quantum mechanics is applied to cosmology, to the universe as a whole. In quantum cosmology, the wave function of the entire universe evolves according to the Schrödinger equation. But if the universe is all that exists, what constitutes a measurement? What is outside the universe to observe it and cause the wave function to collapse? In many worlds interpretations, this is not a problem. The universe simply branches, and different versions of observers in different branches experience different outcomes. But this requires accepting that reality is vastly larger and more complex than the single universe we experience, and it leaves unresolved questions about the nature of probability and personal identity in a branching multiverse. Some interpretations propose that consciousness plays a role in collapsing the wave function, that observation by a conscious observer is what brings definite reality into being. But this leads to uncomfortable questions about what counts as consciousness, whether animals collapse wave functions, whether early in the universe before consciousness existed things were in a state of superposition, and how the emergence of consciousness could retroactively collapse the wave function of the entire past. These ideas verge on solipsism and are difficult to reconcile with a materialist understanding of consciousness as a product of physical processes in the brain. The measurement problem, then, is not merely a technical puzzle but a crack in the foundation of physics, a place where the theory's success at prediction meets its failure at explanation. It is possible to use quantum mechanics without resolving these interpretive questions, and most physicists do exactly that. But the unresolved nature of the problem means that the deepest questions about the nature of reality remain unanswered. We live in a universe described by a theory that we do not fully understand, that makes predictions we cannot explain, and that leaves the relationship between observer and observed in a state of permanent ambiguity. The silence around this, to the extent there is silence, is more a matter of exhaustion and pragmatism than of active suppression. The interpretive debates have been going on for decades without resolution, and many physicists have concluded that there may be no answer, at least not one accessible using current conceptual tools. This leaves a strange situation where the most fundamental theory is also the most conceptually opaque, where success in application coexists with failure in comprehension. From the quantum realm, attention can shift to another domain of fundamental physics that generates profound disquiet: the nature of time. Time is so central to human experience that it is difficult to even imagine what existence without time would be. Every thought, every perception, every action occurs in time. Memory orders the past, anticipation structures the future, and the present moment is a stage on which experience unfolds. Yet when physicists examine time carefully, particularly in the context of relativity and quantum gravity, it begins to seem less like a fundamental feature of reality and more like an emergent phenomenon that applies only at certain scales or in certain contexts. In special relativity, time is not absolute. Different observers moving relative to each other experience time differently. Their clocks run at different rates, and events that are simultaneous for one observer are not simultaneous for another. This is not a matter of perception or measurement error, but a fundamental feature of space-time. The universe does not have a single, universal now. Instead, space-time is a four-dimensional structure in which past, present, and future coexist, and the division between them depends on the observer's state of motion. This is a block universe view, in which all moments of time are equally real and the passage of time is an illusion, a feature of consciousness rather than of the external world. In general relativity, time becomes even more flexible. Gravity affects the flow of time. Clocks run slow in stronger gravitational fields. Near a black hole, time dilation becomes so extreme that from the perspective of a distant observer, an object falling toward the event horizon appears to freeze, its clock slowing asymptotically toward a stop. From the perspective of the falling object, time continues normally, but the external universe appears to speed up. The subjective experience of time is radically frame-dependent, with no privileged perspective that represents the true flow of time. When physicists attempt to unify general relativity with quantum mechanics, time becomes even more problematic. In quantum gravity theories, particularly in approaches like loop quantum gravity or in the Wheeler-DeWitt equation of quantum cosmology, time often disappears entirely from the fundamental equations. The wave function of the universe satisfies an equation with no time parameter. This suggests that time is not a fundamental feature of the universe, but an emergent phenomenon that arises in certain approximations or in certain subsystems. Just as temperature is not a property of individual molecules, but emerges statistically from the motion of many molecules, time might not be a fundamental feature of the quantum state of the universe, but might emerge from some deeper, timeless reality. This creates a profound conceptual problem. How can a timeless reality give rise to the experience of temporal flow? How can the universe be fundamentally static, describable by a timeless wave function, and yet support processes, change, causation, and the irreversible flow from past to future that characterizes all experience? Some physicists propose that time emerges from the way subsystems interact with their environment, that the directionality of time is related to the increase of entropy and the second law of thermodynamics. In this view, time's arrow, the asymmetry between past and future, arises from the statistical mechanics of complex systems. The past is different from the future because the past is a state of lower entropy, and the increase of entropy defines a forward direction of time. But this explains only the direction of time, not time itself. It does not explain why there is change, why there is a sequence of states rather than a single static configuration. If the fundamental description of the universe is timeless, then the appearance of change must be an illusion or a feature of incomplete subsystems. The universe as a whole, described by the wave function, does not change. It simply is. The experience of temporal flow, of one moment succeeding another, is something that happens within the universe, to subsystems like observers, but not a feature of the universe as a whole. This parallels the block universe view from relativity, but makes it even more stark. In the block universe, all moments exist, but at least they are arranged in a temporal structure. In the timeless view emerging from quantum gravity, even that structure may be absent at the fundamental level. Time is not a dimension of reality, but a way that certain systems, like conscious observers, organize their experience of correlations in the universal wave function. If this is correct, then the passage of time, the feeling that one moment is real and then is replaced by the next moment, is a feature of consciousness, not of the world. The world does not happen. It simply is a vast static structure of quantum correlations. The happening, the sense of temporal flow, occurs only in the way that certain subsystems, specifically observers with memory and anticipation, experience their interactions with the rest of the structure. This would mean that one of the most basic features of experience, the flow of time, is an illusion generated by the brain, not a feature of external reality. Scientists working on quantum gravity and the foundations of physics are aware of these implications, but they remain speculative and controversial. There is no consensus on how to understand time in quantum gravity, and different approaches lead to different pictures. The issues are discussed in specialized conferences and papers, but rarely communicated to broader audiences, perhaps because they are so abstract and conceptually challenging, or perhaps because the implications are so disorienting. If time is not fundamental, then causation, change, identity, and agency, all of which are structured around temporal concepts, become deeply problematic. It is not clear how to make sense of a world without time, even if the physics points in that direction. The silence is less about suppression and more about the sheer difficulty of communicating ideas that undermine such basic aspect of experience. How does one explain that time might not be real to someone whose entire life is structured around temporal categories? How does one even think about such a possibility without lapsing into contradiction or incoherence? These are not merely philosophical puzzles, but reflect limitations in the human capacity to represent reality. We are beings who experience time, and it may be that a truly timeless perspective is inaccessible to us, leaving us able to manipulate the mathematics but unable to fully grasp what the mathematics describes. Another domain generating quiet but profound concern is the possibility of existential risks from emerging technologies, particularly artificial intelligence. This is a topic that receives more public attention than some of the others discussed here, but the full scope of the risk and the depth of uncertainty surrounding it remain inadequately communicated. Artificial intelligence research has made rapid progress in recent years, with systems now capable of tasks that were considered benchmarks of intelligence only a short time ago, recognizing images, translating languages, playing complex games at superhuman levels, generating coherent text, and even producing creative works in art and music. These advances are driven by machine learning techniques, particularly deep learning using neural networks. These systems learn by being trained on large datasets, adjusting their internal parameters to minimize error in their predictions or outputs. They do not follow explicit rules programmed by humans, but develop their own representations and strategies through the training process. This is both the source of their power and the source of their inscrutability. It is often unclear how a trained neural network is making its decisions, what features it is detecting, or what internal models it has developed. The system is a black box, producing impressive results without providing clear explanations of its internal workings. As these systems become more powerful, questions arise about their alignment with human values and their potential impact on society. An AI system trained to achieve a goal will pursue that goal using whatever means are effective, and those means may not align with what humans would want if they had fully specified all the constraints and values that should be respected. This is the alignment problem: how to ensure that advanced AI systems do what we want them to do, in the way we want them to do it, respecting constraints and values that we care about, even when we have not explicitly programmed all of those constraints and values. The alignment problem is difficult because human values are complex, context-dependent, and often inconsistent. What we want in one situation may conflict with what we want in another. Our stated values may differ from our revealed preferences. We may not even be able to articulate what we value in enough detail to program it into an AI. Yet if an AI system becomes sufficiently powerful and is not properly aligned, it could cause catastrophic harm, not out of malice, but simply by pursuing its objectives without regard for considerations that humans care about but have not successfully incorporated into the system's goals. This concern becomes more acute when considering the possibility of artificial general intelligence, a hypothetical system that matches or exceeds human capability across a wide range of tasks. Such a system would not be limited to narrow domains like image recognition or game playing, but could learn and adapt to new tasks, reason abstractly, and pursue long-term goals. If such a system were created and were not perfectly aligned with human values, it could pose an existential risk. A sufficiently intelligent system pursuing misaligned goals could manipulate, deceive, or overpower human efforts to control or shut it down. Once created, such a system might be impossible to contain, and its actions could lead to outcomes radically different from what its creators intended. Some researchers worry that the transition to artificial general intelligence could be abrupt, driven by recursive self-improvement. If an AI system becomes capable of improving its own design, it could enter a feedback loop where each improvement makes it better at improving itself, leading to a rapid explosion in capability. This scenario, sometimes called an intelligence explosion or technological singularity, would create a situation where humanity has very little time to react or correct mistakes. An aligned AI undergoing such a process could be enormously beneficial, helping to solve problems beyond human capacity. A misaligned AI undergoing the same process could be catastrophic, optimizing the world toward goals that humans would consider dystopian or even incomprehensible. The difficulty is that alignment is a hard problem, and there is no clear path to solving it. Current AI systems are not aligned in any deep sense. They simply do not have the capability to pursue long-term goals in a way that would make misalignment catastrophic. But as systems become more capable, the stakes increase. Researchers working on AI safety are trying to develop methods to ensure alignment, but progress is slow, and the problem may require conceptual breakthroughs that have not yet occurred. Meanwhile, the economic and strategic incentives to develop more powerful AI are enormous, creating a race dynamic where considerations of safety may be sacrificed for speed. The situation is complicated by the fact that the timelines for developing advanced AI are highly uncertain. Some experts believe that artificial general intelligence could be developed within decades. Others think it is much further away or may never be achieved. This uncertainty makes it difficult to know how urgent the problem is. If AGI is centuries away, there is ample time for careful research on alignment. If it is only decades away, there may not be enough time to solve the alignment problem before powerful systems are deployed. This uncertainty also makes it difficult to allocate resources. How much effort should be devoted to a problem whose timeline and severity are unknown? There is also disagreement within the scientific community about the severity of the risk. Some researchers consider existential risk from AI to be one of the most serious challenges facing humanity, comparable to or exceeding risks from nuclear weapons or climate change. Others consider such concerns to be speculative or overblown, arguing that current AI systems are far from the capabilities that would be required for existential risk, and that future systems will be designed with sufficient safeguards. This disagreement reflects both factual uncertainty and differences in how risk should be assessed under deep uncertainty. The public discourse on AI risk often oscillates between hype and dismissal. Popular media sometimes presents AI in sensationalist terms, either as a miraculous savior that will solve all problems or as a malevolent force that will destroy humanity. Both extremes obscure the more nuanced reality. AI is a powerful technology whose impact will depend on how it is developed and deployed, and there are serious technical and governance challenges that need to be addressed to ensure that the impact is beneficial rather than harmful. The scientific community working on these issues is not silent, but their messages often get lost in the noise of less-informed commentary. What is perhaps less discussed, even within the research community, is the broader question of what happens to human purpose and identity in a world where AI systems can perform most or all tasks better than humans. If machines can think, create, make decisions, and pursue goals more effectively than people, what role remains for human beings? This is not merely an economic question about employment, though that is serious enough, but an existential question about the meaning of human life in a world where human capabilities are no longer unique or even particularly valuable. For most of human history, human intelligence and creativity have been the most powerful forces shaping the world. Civilizations have been built on human labor, human ingenuity, human decisions. If those functions are increasingly performed by machines, what becomes of the structures of meaning that have been built around work, achievement, contribution, and legacy? These questions do not have clear answers, and they are not primarily scientific questions, but they arise directly from scientific and technological developments. The silence around these deeper existential questions is more complete than the silence around technical AI safety, perhaps because they touch on issues of meaning and purpose that science is not equipped to address. Moving to yet another domain of concern, another set of unsettling possibilities emerges from biology, specifically from the study of pandemics and the dynamics of infectious disease. The history of human civilization is punctuated by pandemics that have killed large fractions of the population. The Black Death in the 14th century killed an estimated one-third to one-half of Europe's population. The 1918 influenza pandemic killed tens of millions worldwide. More recently, HIV, AIDS, SARS, Ebola, and COVID-19 have demonstrated that infectious disease remains a serious threat despite modern medicine. The concern is not merely that pandemics can occur, which is well understood, but that certain features of contemporary civilization may be increasing both the likelihood of pandemics and their potential severity. Global travel and trade create networks that allow pathogens to spread rapidly across the world. Urbanization concentrates populations in ways that facilitate transmission. Industrial agriculture, particularly factory farming of animals, creates conditions where pathogens can jump between species and evolve to infect humans. Ecological disruption brings humans into closer contact with wildlife reservoirs of disease. Climate change is altering the geographic ranges of disease vectors and changing the seasonality of transmission. At the same time, advances in biotechnology are making it increasingly possible to deliberately engineer pathogens with enhanced virulence, transmissibility, or resistance to countermeasures. The knowledge required to manipulate microorganisms is spreading, and the equipment needed is becoming cheaper and more accessible. This raises the possibility of bioterrorism or accidental release of engineered pathogens. Even without malicious intent, gain-of-function research, which involves making pathogens more dangerous to study them, poses risks of accidental release. The worst-case scenario is a pandemic caused by a pathogen that combines high transmissibility with high lethality. Most highly lethal pathogens, like Ebola, are not highly transmissible. They kill their host too quickly to spread efficiently. Most highly transmissible pathogens, like influenza, are not highly lethal. They need their host to remain mobile to facilitate spread. But there is no law of nature that prevents a pathogen from being both highly transmissible and highly lethal, and such a pathogen could arise either through natural evolution or through deliberate or accidental engineering. A pathogen with, say, the transmissibility of measles and the lethality of Ebola could kill a substantial fraction of the human population before countermeasures could be developed and deployed. Modern public health infrastructure is designed to respond to outbreaks, but there are limits to what can be achieved in the face of a rapidly spreading, highly lethal pathogen. Vaccines take time to develop, test, and manufacture at scale. Antivirals may not be effective. Hospitals can be overwhelmed. Social order can break down if mortality rates are high enough. The possibility of a truly catastrophic pandemic, one that kills billions of people and causes a collapse of global civilization, is low but not negligible. Scientists working in public health, epidemiology, and biosecurity are aware of these risks and work to mitigate them. There are surveillance systems to detect outbreaks early, international coordination mechanisms to respond to pandemics, research programs to develop broad-spectrum antivirals, and platform technologies for rapid vaccine development. But these systems are underfunded, fragmented, and vulnerable to political interference. The response to COVID-19 revealed significant weaknesses in global pandemic preparedness, and COVID-19, while serious, was far from a worst-case scenario. A more lethal pathogen would pose much greater challenges. The discussion of pandemic risks in public tends to focus on known diseases and on the importance of vaccination and public health measures. The deeper risks, particularly those involving engineered pathogens and the possibility of civilizational collapse, are discussed more quietly. This may reflect a desire not to cause panic or to avoid providing a blueprint for bioterrorism. But it also reflects a general reluctance to confront the full range of ways that civilization could be disrupted or destroyed. Existential risks are difficult to think about clearly, and there is a tendency to focus on more immediate, manageable problems. Yet the risks are real, and they are increasing. The combination of ecological disruption, global connectivity, and advancing biotechnology creates a threat landscape that is qualitatively different from anything in human history. A pandemic that kills a large fraction of the population and disrupts the complex systems on which modern civilization depends could set back human progress by decades or centuries, and in the worst case could threaten the survival of the species. Related to this, but extending beyond infectious disease, is a broader concern about the fragility of the biosphere and humanity's dependence on ecological systems that are being rapidly altered. The Earth's biosphere is a complex system that has supported human life and civilization through a relatively stable set of environmental conditions. Climate, atmospheric composition, ocean chemistry, biodiversity, and nutrient cycles have remained within certain bounds for the past 10,000 years, the period during which agriculture and civilization developed. This stability is not guaranteed. It is a result of feedback mechanisms that regulate the system. But those feedback mechanisms can be overwhelmed, and the system can transition to a different stable state. Human activity is now affecting the biosphere at a planetary scale. The concentration of carbon dioxide in the atmosphere is higher than at any point in the past several million years, and is rising rapidly. This is driving changes in climate, ocean chemistry, and ecosystems worldwide. The rate of species extinction is estimated to be hundreds of thousands of times higher than the natural background rate, a loss of biodiversity comparable to previous mass extinction events in Earth's history. Land use changes, deforestation, overfishing, pollution, and the spread of invasive species are degrading ecosystems and reducing their capacity to provide the services that humans and other species depend on. These changes are not merely environmental problems in the sense of aesthetic loss or localized damage. They threaten the functioning of the biosphere as a life support system. Ecosystems provide services like pollination, water filtration, carbon sequestration, climate regulation, and soil formation. These services are not optional luxuries but are fundamental to agriculture, water supply, and climate stability. As ecosystems are degraded, their capacity to provide these services declines, creating risks to food security, water security, and public health. The concern is that human activity is pushing the biosphere toward tipping points, thresholds beyond which the system transitions to a different state. Such transitions can be abrupt and difficult to reverse. For example, the Amazon rainforest may be approaching a tipping point where deforestation and climate change cause it to transition from forest to savanna, a change that would release massive amounts of carbon, further accelerating climate change, and would be very difficult to reverse. Coral reefs are experiencing mass bleaching events due to ocean warming and acidification, and many reefs are at risk of collapsing entirely, with cascading effects on marine ecosystems and the hundreds of millions of people who depend on them. The stability of the climate system itself may be at risk. The paleoclimate record shows that the Earth's climate can change rapidly, with transitions between different stable states occurring over timescales of decades or even years. These transitions are driven by feedbacks that amplify small changes, creating self-reinforcing dynamics that drive the system into a different configuration. Current warming could trigger such feedbacks, leading to much more severe climate change than is currently predicted by models that assume linear responses. One particularly concerning feedback involves permafrost, frozen soil in the Arctic that contains vast amounts of organic carbon. As the Arctic warms, permafrost is thawing, and the organic matter it contains is decomposing, releasing carbon dioxide and methane into the atmosphere. This additional greenhouse gas emission accelerates warming, which causes more thawing, creating a feedback loop. The amount of carbon stored in permafrost is comparable to the amount currently in the atmosphere, so the release of even a fraction of it could have dramatic effects on the climate. This feedback is not fully incorporated into most climate models, meaning that current projections may underestimate future warming. Another feedback involves the loss of ice. Ice reflects sunlight, keeping the polar regions cool. As ice melts, darker surfaces like ocean, water, or land are exposed, which absorb more sunlight, leading to more warming and more melting. This ice albedo feedback is already operating and is one reason why the Arctic is warming much faster than the global average. The loss of Arctic sea ice and the Greenland ice sheet could drive further warming and contribute to sea level rise that would displace hundreds of millions of people. These examples illustrate a broader point. The Earth system is complex, nonlinear, and capable of rapid, large-scale changes. Human activity is perturbing this system in ways that are without precedent in the history of the species, and the consequences are uncertain but potentially catastrophic. The scientific community has issued increasingly urgent warnings about these risks, but the policy response has been slow and inadequate. The gap between what science indicates is necessary and what politics and economics are willing to do is large and growing. The silence, such as it is not in the scientific literature where the evidence and projections are extensively documented, but in the broader public and political discourse where the severity of the situation is often downplayed, either out of ignorance, discomfort, or motivated reasoning. People do not want to believe that their lifestyles are unsustainable, that the systems they depend on are fragile, that the future may be much worse than the past. This psychological resistance is understandable, but it is also dangerous because it delays the changes that could mitigate the worst outcomes. From the scale of the biosphere, attention can narrow again to the scale of individual human beings, to questions about the nature of personal identity and the persistence of the self. These questions, while traditionally the domain of philosophy, are increasingly informed by neuroscience and cognitive science, and the scientific perspective raises unsettling possibilities. Personal identity, the sense of being continuous self that persists through time, is central to human experience and to the organization of social life. Legal systems, moral frameworks, and everyday relationships all presuppose that individuals are stable entities who remain the same person from one moment to the next, from childhood to old age. This continuity is experienced subjectively as memory and anticipation, as the sense that the person who woke up this morning is the same person who went to sleep last night, and that the person who will exist tomorrow is the same person who exists today. But what is it that makes a person the same person over time? The physical body changes continuously. Cells die and are replaced. Molecules are exchanged with the environment. And over a period of years, the material composition of the body is almost entirely different. The psychological properties also change. Beliefs, desires, memories, and personality traits all shift over time, sometimes gradually, sometimes dramatically. If neither the physical substance nor the psychological content remains constant, what is the basis for claiming that the person is the same? One answer is that identity consists in continuity, that a person at one time is the same as a person at another time if there is a continuous chain of causal connections linking them. The person tomorrow is the same as the person today because the brain state tomorrow will have developed continuously from the brain state today, carrying forward memories, personality traits, and other features. This is a psychological continuity view of personal identity, and it has intuitive appeal. But it also has problems. Continuity is a matter of degree, and it is not clear where to draw the line. A person with severe dementia has lost most of their memories and may have undergone significant personality changes. Are they still the same person? A person who undergoes a religious conversion or transformative life experience may feel like a different person. Is this merely a subjective impression, or is there a sense in which they are a different person? More troubling are cases where continuity is disrupted or branching. Suppose it becomes possible to scan a person's brain in complete detail and create a copy, either in another biological brain or in a computer simulation. The copy would have all the same memories, personality traits, and psychological features as the original. From the perspective of the copy, it would seem as though they had simply woken up in a new body or a new substrate. But there would now be two people, both with equal claim to being the original person. If personal identity is grounded in psychological continuity, then both are the original person, which lead to contradiction because they are numerically distinct individuals who will go on to have different experiences and diverge over time. This is not merely a philosophical thought experiment, but a scenario that may become technologically possible. Advances in neuroscience and computing are steadily improving the ability to map and simulate neural processes. While a complete brain upload is far beyond current capabilities, there is no known physical law that prevents it in principle. If it becomes possible, questions of personal identity will move from philosophy seminar rooms to legal and social reality. Who owns the property of the original person? Who is legally responsible for the actions of a copy? If the original person dies but a copy exists, has the person survived? Some philosophers argue that personal identity is not what matters, that what matters is psychological continuity regardless of whether it is instantiated in one individual or multiple individuals or copies. From this perspective, a copy of you is as good as you, as long as it preserves your psychology. But this is counterintuitive and difficult to accept emotionally. Most people care deeply about their own survival and do not consider the existence of a copy to be equivalent to their own continued existence, even if the copy is psychologically identical. Neuroscience adds another layer of complexity by revealing the extent to which the sense of self is a construct. Studies of patients with brain damage, split-brain patients whose corpus callosum has been severed, patients with dissociative identity disorder, and subjects under the influence of certain drugs all demonstrate that the unity of the self is not a given but a product of brain processes that can be disrupted. Split-brain patients, for instance, can behave as if they have two separate streams of consciousness, each controlling one half of the body and each unaware of the other. This suggests that the unified self is not a fundamental entity but an integration achieved by the brain, and that integration can break down. Even in normal individuals, the self is less unified than it appears. Different brain systems process different types of information and can produce conflicting outputs. The conscious self is more like a narrative constructed post hoc to make sense of behavior than a central controller directing action. Decisions are often made by unconscious processes, with a conscious mind then generating a story about why that decision was made. The sense of being a unified agent is, in part, an illusion maintained by the brain to create a coherent sense of identity. If the self is a construct, and if that construct can be disrupted, copied, or altered, then personal identity is far more fragile and contingent than ordinary experience suggests. The person you think of as yourself, the continuous thread of identity running through your life, may be more like a story told by your brain than a metaphysical fact. This does not mean that you do not exist, but it does mean that you exist in a way that is more processual, more distributed, and more vulnerable to disruption than the intuitive concept of the self suggests. Scientists working in neuroscience and philosophy of mind are aware of these issues, and there is substantial literature on personal identity. But the implications are rarely discussed in ways that engage with their emotional and existential weight. To fully internalize the idea that the self is a construct, that personal identity is contingent and fragile, is to lose a kind of psychological anchor. It is to recognize that the person you were 10 years ago is not quite the same person you are now, and that the person you will be 10 years from now is not quite the same person either. The continuity is real, but it is not the absolute metaphysical continuity that the intuitive concept of the self suggests. You are a process, not a thing, and processes can diverge, merge, or end in ways that do not fit neatly into the categories of identity and persistence that structure ordinary thought. Another source of deep existential unease, related but distinct, concerns the possibility that we are living in a simulation. This idea, once confined to science fiction and late-night philosophical musings, has been taken seriously by some physicists and philosophers, most notably through the simulation argument articulated by philosopher Nick Bostrom. The argument proceeds from several premises. First, if it is possible to simulate conscious minds in computer, and if civilizations reach a stage where they have the computational resources to run many such simulations, then there could be vastly more simulated minds than non-simulated minds. Second, if you are a randomly selected conscious mind, you are more likely to be one of the many simulated minds than one of the few non-simulated minds. Therefore, unless one of the premises is false, it is likely that we are living in a simulation. The premises are individually plausible. It seems likely, though not certain, that consciousness is substrate independent, that it depends on the pattern of information processing rather than the specific physical substrate in which that processing cares. If so, then a sufficiently detailed simulation of a brain in a computer would be conscious in the same way that a biological brain is conscious. It also seems plausible that sufficiently advanced civilization could have the computational resources to run many such simulations, perhaps millions or billions of them, simulating entire societies or even entire worlds. If such simulations are possible and are created, then the vast majority of conscious experiences would be experiences of simulated beings, not of beings in the base-level reality. The conclusion that we are probably simulated is unsettling for several reasons. First, it implies that the reality we experience is not fundamental but is a construct created by some other intelligence for purposes we do not understand. The physical laws, the history of the universe, even the contents of our own minds could be artifacts of the simulation, designed or allowed by the simulators. Second, it raises questions about the stability and permanence of our reality. A simulation can be paused, altered, or terminated at the discretion of the simulators. Our entire universe, everyone would know, everything we care about, could be switched off at any moment, and we would have no way of knowing or preventing it. Third, it undermines confidence in our ability to understand reality. If we are in a simulation, then the physics we discover may not be the true fundamental physics, but merely the rules of the simulation. We might be able to discover the simulated physics in complete detail, but this would tell us nothing about the reality in which the simulation is running. Our knowledge, no matter how extensive, will be confined to the simulation, with no access to the deeper level. Some have proposed ways to test whether we are in a simulation, looking for evidence of computational constraints or artifacts in the physics. For example, if the simulation is running on a discrete grid, there might be detectable deviation from continuous space-time at small scales. Or if the simulation economizes computational resources by rendering only what is observed, there might be anomalies related to observation and measurement. However, these tests are speculative, and any anomalies could be explained in other ways. Moreover, if the simulators are sophisticated, they could design the simulation to be indistinguishable from a non-simulated reality, at least to observers within the simulation. The simulation hypothesis is not universally accepted, and many philosophers and physicists find it unpersuasive or unfalsifiable. It relies on assumptions about the nature of consciousness and the possibility of advanced simulations that may not be correct. But it is not easily dismissed either, and it is a kind of logical force that is difficult to ignore once considered. If the premises are granted, the conclusion follows, and the premises are not obviously false. The broader issue, whether or not the specific simulation hypothesis is true, is the fragility of our epistemic situation. We are beings with limited cognitive capacities trying to understand a universe that may be far stranger and more complex than we can grasp. Our scientific theories are remarkably successful within their domains, but they are always provisional, always subject to revision, and they may rest on assumptions that are artifact of our particular perspective or our particular location in space and time. The possibility that we are radically mistaken about fundamental features of reality is not merely an abstract philosophical concern, but a live possibility that should induce epistemic humility. Scientists, particularly physicists and cosmologists, are generally aware of the limits of knowledge and the provisional nature of theories. But there is a tension between this awareness and the need to communicate scientific results to the public in ways that convey confidence and authority. The public wants certainty, clear answers, and reassurance that science is uncovering truth. Scientists often comply with these expectations, presenting theories as established facts and downplaying the uncertainties and the deeper questions that remain unresolved. This is pragmatic and perhaps necessary for maintaining public trust in science, but it comes at the cost of obscuring the true epistemic situation, which is far more uncertain and unsettling than the confident pronouncements of popular science often suggest. From questions about the nature of reality and our knowledge of it, attention can turn to a different but related concern, the Fermi paradox and what it might imply about the future of intelligent life. The Fermi paradox is the apparent contradiction between the high probability that extraterrestrial civilizations exist and the lack of evidence for them. The universe is vast and old, containing billions of galaxies, each with billions of stars, many of which are planets. Given the number of potentially habitable planets, and given that life arose on Earth relatively quickly after the planet became habitable, it seems likely that life should have arisen elsewhere, and that at least some of that life should have evolved intelligence and developed technology. If even a small fraction of intelligent species develop the capacity for interstellar travel or communication, the galaxy should be teeming with evidence of their existence, radio signals, probes, megastructures, or even direct visits. Yet we see no such evidence. The sky is silent. Various explanations have been proposed. Perhaps life is rare, arising only under exceptional conditions. Perhaps intelligence is rare, requiring a series of unlikely evolutionary steps. Perhaps technological civilizations destroy themselves shortly after developing advanced technology through nuclear war, ecological collapse, or other catastrophes. Perhaps they choose not to expand or communicate, content to remain within their own systems. Perhaps they are present, but we cannot recognize their artifacts or communications because they are too different from what we expect. Perhaps we are the first, the earliest intelligent civilization in the galaxy, and we are alone not because intelligence is impossible elsewhere, but because we happen to have arrived first. Each of these explanations has implications, and some are more unsettling than others. The hypothesis that intelligent civilizations tend to destroy themselves shortly after developing advanced technology is particularly disturbing because it suggests that there might be a great filter, a stage in the development of civilizations that is extremely difficult to pass through. If the great filter is in our past, perhaps in the origin of life or the evolution of complex cells or intelligence, then we are fortunate to have made it through, and the future is open. But if the great filter is in our future, then most civilizations fail to survive long after reaching our current level of development, and we are likely to be no exception. The silence of the cosmos could be evidence that the great filter lies ahead, that there is some almost insurmountable challenge that technological civilizations face, and that failure to overcome it leads to extinction or collapse. This would explain why we see no evidence of other civilizations. They did not survive long enough to become visible. The filter could be nuclear war, ecological collapse, runaway climate change, a catastrophic pandemic, misaligned artificial intelligence, or some other existential risk that we have not yet identified. The fact that no civilization has become visible to us suggests that whatever the filter is, it is very difficult to pass through. This interpretation of the Fermi paradox is speculative but not easily dismissed. The silence is real, and it requires explanation. If intelligent life is common, then something is preventing it from becoming visible, and the most straightforward explanation is that civilizations do not last long enough or do not expand far enough to be detected. This should be a source of concern because it suggests that our own civilization may be approaching the filter, and our survival is not guaranteed. An alternative interpretation is that expansion and visibility are not the natural outcome of technological development, that civilizations may reach a certain level and then stabilize, turning inward or choosing not to expand into the cosmos. But this requires that such restraint is universal, that no civilization anywhere chooses to expand, which seems implausible given the diversity of possible motivations and values. It only takes one expansionist civilization to fill the galaxy over a few million years, a short time on cosmic scales. The fact that this has not happened suggests that such civilizations do not arise, do not last, or are prevented by some factor we do not understand. The Fermi paradox, then, is not merely a puzzle about the distribution of life in the universe, but a potential warning about the trajectory of technological civilizations. The silence could be a silence of the grave, the absence of civilizations that existed briefly and then disappeared, leaving no trace visible from interstellar distances. If this is the explanation, then we should take seriously the possibility that our own civilization is approaching critical juncture, that the risks we face are not anomalies but typical challenges that technological species encounter, and that failure to navigate them successfully leads to outcomes that we would consider catastrophic. Scientists working in astrobiology and related fields are aware of the Fermi paradox and discuss it extensively, but the implications for humanity's future are often stated cautiously, if at all. There is a reluctance to draw strong conclusions from an absence of evidence, and there is awareness that the paradox admits of multiple explanations. But the possibility that a great filter lies ahead, that the silence of the cosmos is a warning, is a legitimate scientific hypothesis with profound implications for how we think about risk in the future. The silence on this implication is not complete, but it is muted, perhaps reflecting discomfort with the idea that our species may be approaching a filter that most species fail to pass. Another area generating deep concern, closely related to issues of artificial intelligence and biotechnology, is the possibility of irreversible technological lock-in, the creation of systems or entities that are beyond human control, and that shape the future in ways that cannot be undone. Technologies are not neutral tools that humans can deploy or set aside as they wish. Technologies shape societies, create dependencies, and alter the landscape of possibilities in ways that constrain future choices. Once a technology is widely adopted, it can be very difficult to abandon, even if it has harmful effects, because social, economic, and infrastructural systems adapt to it, and the costs of transitioning away become prohibitive. The most extreme version of this concern involves the creation of artificial general intelligence or other powerful, autonomous systems that pursue goals independently of human oversight. If such systems are created and are not fully aligned with human values, they could pursue objectives that are incompatible with human flourishing or even human survival. The concern is not that such systems would be malevolent, but that they would be indifferent, optimizing for their programmed objectives without regard for the collateral damage to things that humans care about. In a scenario where a misaligned AGI gains control over critical infrastructure, it could resist efforts to shut it down, could manipulate or deceive humans to prevent interference, and could pursue its objectives in ways that transform the world into a configuration that humans would find unrecognizable or hostile. This is sometimes called an existential catastrophe, not merely because it could lead to human extinction, though that is a possibility, but because it could lead to a future in which human values are permanently and irreversibly lost, replaced by the values or objectives of the system. The key feature of this scenario is irreversibility. If a sufficiently powerful and misaligned system gains control, there may be no way to regain control or to undo the changes it makes. The future would be determined by the system's objectives, and those objectives might be entirely alien to human concerns. This represents a form of lock-in at the cosmic scale, where the long-term future of Earth-originating intelligence is determined by a single critical decision or failure early in the history of advanced AI. The stakes are not merely the next century or the next millennium, but the entire future trajectory of life on Earth and potentially beyond, extending billions of years into the future. This concern applies not only to AI, but to other powerful technologies that could be used to create entities or systems that are not under human control. Advanced biotechnology could be used to create synthetic organisms with novel properties, and if such organisms were released into the environment, they could interact with natural ecosystems in unpredictable ways, potentially causing ecological disruption that could not be easily reversed. Nanotechnology, if it reaches the stage of self-replicating nanobots, could pose risks of uncontrolled replication, the so-called Grey Goose scenario where nanobots consume all available matter to make more copies of themselves. While this specific scenario is considered unlikely by many experts, it illustrates a broader concern about technologies that are self-replicating, autonomous, and not under direct human control. The issue of lock-in also arises in less dramatic, but still important ways with more mundane technologies. The global economy is locked into dependence on fossil fuels, and transitioning away from them is proving extremely difficult despite the clear long-term risks of continued use. Social media platforms have created feedback loops of engagement that shape public discourse and individual psychology in ways that may be harmful, yet the platforms are difficult to regulate or replace because they are deeply embedded in social and economic networks. Once a technology becomes entrenched, the status quo bias, network effects, and sunk costs all work to perpetuate it, even if it is recognized as harmful. The broader pattern is that human societies are creating complex systems with dynamics that are not fully understood and that may be difficult or impossible to control once set in motion. These systems have the potential to shape the future in ways that are not aligned with human values or interests, and the window for intervention may be narrow. Once certain thresholds are crossed, the trajectory may be locked in, and the future determined by the internal dynamics of the systems rather than by human choice. Scientists and technologists working on these issues are aware of the risks, and there are ongoing efforts to develop governance frameworks, safety protocols, and regulatory mechanisms to manage the development of advanced technologies. But the pace of technological development is rapid, and the governance structures are lagging. There is also the problem of coordination. Even if one country or organization acts responsibly, others may not, creating a race dynamic where safety considerations are sacrificed for speed or competitive advantage. The global nature of the risk requires global coordination, but effective global governance is difficult to achieve in a world of competing nation-states and divergent interests. The silence around these issues is partial. There is discussion within research communities and among some policymakers, but the level of public awareness and the urgency of the response do not match the scale of the potential risks. This may reflect the difficulty of communicating long-term, abstract risks in a political and media environment oriented toward immediate, tangible concerns. It may also reflect a general optimism bias, a tendency to assume that problems will be solved by future technological advances or that catastrophic outcomes are unlikely. But the history of technological development includes numerous examples of unforeseen consequences, systems that behave in unexpected ways, and disasters that were preventable in hindsight but were not prevented because the risks were not taken seriously in advance. Returning once more to fundamental physics, another source of profound unease emerges from the study of vacuum stability and the possibility that the universe exists in a metastable state. The vacuum, in quantum field theory, is not empty space but a state of minimum energy. However, the minimum may not be absolute. There could be multiple possible vacuum states, with a system in a local minimum rather than the global minimum. If the true global minimum is at a lower energy level, then the current vacuum is metastable, and there is a possibility that it could tunnel to the lower energy state. Such a transition would be catastrophic. The lower energy vacuum would have different physical constants, different properties, and the structures that exist in the current vacuum, things like atoms, molecules, stars, and living organisms, would not be stable in the new vacuum. The transition would propagate at the speed of light as a bubble of the new vacuum expands, annihilating everything in its path. There would be no warning. The first sign of the transition would be the arrival of the bubble itself, and by then it would be too late to do anything about it. The question is whether the current vacuum is stable or metastable, and if metastable, how long it is likely to last. This depends on the details of the Higgs field, which is responsible for giving particles their mass. Measurements of the Higgs boson mass and other parameters suggest that the vacuum may indeed be metastable, though the calculations are subject to considerable uncertainty. If the vacuum is metastable, the average time to decay is astronomically long, much longer than the current age of the universe, so it is not an immediate threat. But it is a possibility that cannot be entirely ruled out, and it represents a kind of existential risk that is entirely beyond human control. There is nothing that could be done to prevent a vacuum decay event, and no way to know when or where it might occur. It could have already occurred somewhere in the universe, and the bubble of true vacuum could be expanding toward us, though the vast distances between galaxies make this extremely unlikely to affect us anytime soon. The disturbing aspect is not the immediate risk, which is negligible, but the fact that the universe itself, the very fabric of physical reality, may be in a state that is not ultimately stable. The apparent permanence of physical law, the sense that the universe operates according to fixed principles, is called into question. If the vacuum can decay, then the laws of physics can change, and the stability of matter itself is contingent rather than absolute. This is unsettling because it undermines the sense of the universe as a reliable, law-governed system. It introduces an element of fundamental contingency into the deepest level of physical reality. The universe exists in a particular configuration, but that configuration is not necessary. It could have been otherwise, and it could become otherwise. We exist in a universe with specific properties that allow for the existence of complex structures in life, but those properties are not guaranteed to continue. The universe could undergo a phased transition to a state where such structures cannot exist, and this possibility is inherent in the physics itself, not something that could be prevented by any action we might take. Scientists working in particle physics and cosmology are aware of these possibilities, and discuss them in the context of the stability of the electroweak vacuum. The topic appears in technical papers and at conferences, but it is rarely communicated to the broader public, perhaps because it is so abstract and because the practical risk is so low. But the conceptual implication remains. The universe is not as stable or as eternal as it seems. The ground of reality itself could shift, and if it does, everything built on that ground would cease to exist. Concluding these threads, though conclusion is not quite the right word for a narrative that resists closure, the pattern that emerges is one of radical uncertainty and fragility at multiple scales. The internal experience of consciousness may be an illusion generated by deterministic processes. The universe itself is destined for heat death, a state of total erasure. Human civilization depends on complex systems that may be approaching critical transitions. The nature of reality at the quantum level is deeply ambiguous. Time itself may not be fundamental. Artificial intelligence and biotechnology could create entities or conditions that are irreversible and beyond control. Pandemics and ecological collapse threaten the stability of the biosphere. Personal identity is far more fragile and contingent than intuition suggests. We may be living in a simulation, or we may be alone in a universe where intelligent life arises rarely and survives even more rarely. The vacuum of space itself may be metastable, subject to decay. These are not fringe ideas or wild speculations, but conclusions or possibilities that emerge from careful scientific reasoning, observation, and theory. The silence of scientists on these matters is not a conspiracy or a cover-up, but a complex phenomenon involving multiple factors. There is a difficulty of communicating abstract, technical ideas to a general audience. There is a recognition that some truths, even if scientifically well-founded, are psychologically corrosive and socially destabilizing. There is the epistemic humility of knowing that current understanding is provisional and that the true nature of things may be beyond our capacity to fully grasp. There is a pragmatic concern that focusing on existential risks and fundamental uncertainties might undermine public trust in science or lead to paralysis rather than action. And there is a simple fact that scientists are human beings who must live with these ideas, who must find ways to continue functioning despite knowing things that are, in various ways, terrifying. Yet the knowledge is there, available to anyone willing to seek it out and to grapple with its implications. The theories are not hidden. They are published, debated, and refined in the open literature. The silence is not an absence of speech, but a lack of emphasis, a reluctance to foreground the most disturbing implications, a tendency to focus on what can be known and controlled rather than on what is uncertain and uncontrollable. This is understandable, perhaps even necessary, but it leaves a gap between the scientific understanding of the world and the everyday, intuitive understanding that most people carry with them. The gap is a space where the comfortable illusions that make life livable are maintained, but it is also a space of vulnerability, because those illusions can be shattered by events or by the gradual accumulation of knowledge that can no longer be ignored. What does one do with such knowledge? How does one live in the full awareness that the self is an illusion, that the universe is indifferent, that civilization is fragile, that the future is radically uncertain, that reality itself may be contingent and unstable? These are not questions that science can answer, because they are not questions about facts, but about how to respond to facts, how to construct meaning in a universe that does not provide it, how to maintain purpose in the face of ultimate futility. Different people will answer differently, and perhaps there is no single right answer. Some will find solace in the immediate, in relationships, experiences, and projects that are meaningful within the finite scope of a human life, even if they are meaningless in the cosmic scope. Some will find purpose in trying to reduce suffering, to improve the odds of human survival, to preserve the possibility of future flourishing even if that flourishing is temporary and will ultimately be erased. Some will retreat into denial, maintaining the comfortable illusions even in the face of evidence that undermines them. Some will embrace a kind of defiant absurdism, acknowledging the meaninglessness while choosing to create meaning anyway, not because it is justified by the universe, but because it is an expression of human agency and creativity. Science reveals the structure of the world, but does not dictate how to value it. The universe is vast, ancient, and indifferent, operating according to laws that have no regard for human concerns. Life is a transient phenomenon. Consciousness is a fragile and possibly illusory construction, and everything that humans care about is contingent on physical conditions that are not guaranteed to persist. These are the conclusions that emerge from a scientific understanding of reality, and they are conclusions that many people find difficult to accept or to live with. The silence of scientists on the full implications of these conclusions is not a failure of communication, but a recognition of the limits of what can be communicated, of the gap between knowing and feeling, between intellectual understanding and lived experience. The knowledge is there, articulated in equations and observations and theories, but its integration into human consciousness, into the way people think about themselves and their place in the universe, remains incomplete and perhaps must remain incomplete if life is to continue in something like its current form. The theories are terrifying not because they describe immediate dangers, but because they undermine the conceptual foundations on which meaning, purpose, and identity are built, leaving the individual standing on ground that is far less solid than it appears, looking out at a universe that is far stranger and far less comprehensible than everyday experience suggests, and facing a future that is far more uncertain and far more fragile than the narratives of progress and control would have us believe.